So in this video, we're going to continue working on substitution here, start doing some definite integrals and some more complicated indefinite integrals of substitution. So let's just do a definite integral first of all. I'm just going to write this down. So let's suppose, whoops, we want to do an integral from 2 to 4. So for bounds, that makes this a definite integral. We're going to do x squared e to the x cubed plus 2 dx. So a definite integral here. We're going to use substitution here. So what I see is e to the something. I would really like that something to be like u here. So what I'm going to do is I'm going to let u equal the exponent on e. That's the x cubed plus 2. And then du, du is going to be the differential or derivative of x cubed plus 2. That's 3x squared, and then I need my dx. And so what I'd like to do is rewrite my integral with e to the u, which I've got, but I want to have a 3x squared dx. So I just have dx here, but I do have the x squared up in here, up in front, so I need to get the 3 as well. So what I'm going to do, I'm going to write the e to the x cubed plus 2, and then I'd like to have 3x squared dx. Now I've got my x squared already. This 3 just sort of appeared here. So I need to compensate for that. Multiplying by 3, I can sort of compensate by multiplying by 1/3 out in front. And so now what I get is an integral, 1/3 times the integral. E to the x cubed plus 2 is e to the u. And then the 3x squared dx is du. This is an integral that I can do, but I've got a little bit of trouble with the bounds here. So there's multiple ways to deal with the bounds. In this case, what I'm going to do is take this 2 and 4, which are really x values, and convert them to u values. So I'm going to think about here this 2, that means x equals 2. Well, what's u when x is 2? Well, u is x cubed plus 2. So that's 2 cubed plus 2. That's going to be 8 plus 2, that's 10. So my lower bound is going to be 10, because when x is 2, u is 10. My upper bound of 4, so if x is 4, u should be 4 cubed plus 2. 4 cubed is going to be 64. I add 2 and I get 66. So my upper bound is going to be 66. So I had to convert my bounds to be in terms of u. And now what I'm going to get is 1/3. If you do an antiderivative e to the u, it's sort of a nice case. It gives us e to the u back. And then these bounds, sometimes I'll write u equals 10 and u equals 66 instead of just 10 and 66, just to get a kind of emphasize that we're plugging in values of u as opposed to x. And so what I do is I do 1/3, and then I'm going to do e to the 66 minus e to the lower bound, which is 10. And a lot of times I might write this as just e to the 66 minus e to the 10 over 3. So there's our answer to this definite integral. Should be a number. This is an exact value. You could create a decimal out of that if you would like. Okay, next question here. I'm going to look at another definite integral. I'm going to go 0 to 1. And we're going to do x plus 2 times x squared. Let's write that a little more cleanly. X squared plus 4x plus 1. Take that quantity cubed dx. So this time, instead of converting the bounds from x to u, what I'm going to do is just sort of do an indefinite integral without the bounds first and plug in the original x values into that. So just a little bit different take on this. So what I'm going to look at is the indefinite integral, x plus 2 times x squared plus 4x plus 1 cubed dx. So I'm going to do this. Now here, there's a couple of approaches here. One thing you could do is sort of expand this out, the x squared plus 4x plus 1, expand that out, do the cube, multiply it out, multiply by x plus 2, you'd get a degree, I guess, 7 polynomial here with a bunch of other stuff. You'd have a polynomial. You could integrate that. That would work, but it sounds like, a fair amount of effort here. So instead, what I'm going to do is I have this x squared plus 4x plus 1 to the 3rd. I'm going to let u be x squared plus 4x plus 1. Then du, well, what's our derivative? It's 2x plus 4, and then we get a 0, times dx. So that's really our derivative here. Now, we don't have 2x plus 4 here, but if you look at this, that's really 2, factor the 2 out, times x plus 2 dx. So we have an x plus 2, so this is something we can actually work with here. So what we're going to get, I'm going to rewrite this as x squared plus 4x plus 1 cubed, and then I'd like to have this times 2 x plus 2 dx. And this 2 here just sort of showed up at this point randomly because I want a 2 there, so I can't just multiply by the 2. I have to compensate for that by multiplying by 1/2 out in front. So the 2 times 1/2 would cancel here, and it gave us what we started with. Now I'm going to convert this to u. So I'm going to get an integral x squared plus 4x plus 1 is u, so it becomes u cubed. And then I'm just going to get a du with sort of this right-hand part. And so what I get then is 1/2. Integrate u cubed gives me u to the 4th over 4. I guess as an indefinite integral, I should write plus c. When we do the definite part of this, we're plugging our values. I'm going to choose c to be 0 just to make things simpler. So I don't really need the c, but I'm going to put it anyway. And then I'm going to convert that u into x. So 2 times 4 on the bottom, that's 8. And then my u is x squared plus 4x plus 1. And then that's to the 4th plus c. So this was an indefinite integral, not the question we were asked. We want to do a definite integral. But now what we can do is take this original definite integral, and we can just take an antiderivative of the inside. That's this answer we got over here, but we can choose any constant we want. So we're going to evaluate top and bottom. We'll subtract those c's. I'm going to choose my c to be 0 just because it's simpler. And so this will give us x squared plus 4x plus 1 over 8. Whoops, x squared plus 4x plus 1 to the 4th. And then I have to evaluate that at x equals 0 and x equals 1. And again, I wrote the x equals for emphasis that that's not u, that's x. And so now I'm going to plug in x equals 1. I'm going to get 1 squared is 1, plus 4 times 1 is 4, plus 1. So I get 1 plus 4 plus 1 to the 4th over 8, minus plug in 0. That gives me, I guess, 0 plus 0 plus 1 over 8. 0 plus 0 plus 1 to the 4th. And then what I'm going to get, let's see, 1 plus 4 plus 1, that's 6 to the 4th over 8, minus 1 to the 4th is just 1 over 8. So let's see, 6 to the 4th is 36 squared. That's going to be a 1296 minus 1 over 8. So I'm going to end up with an answer of 1295 over 8. So I should get a number out of this calculation. Okay, couple more here. These are going to be indefinite integrals. You could create bounds and do them as definite integrals, but I just want to sort of focus on what to make u in some maybe more complicated situations. So I'm going to do an antiderivative of x times the square root of x plus, let's do 3 dx. So here's what I want to find. Now, looking at this, I guess what I might try and do is bring the x inside the square root. That's not going to help out a whole lot here. So we bring the x inside. That x is square root of x squared times square root of x plus 3. Note, x is only square root of x squared if x is positive. We don't have bounds, but I'm just going to kind of assume that it'll work out that way. Sometimes I should be more worried about the signs than I am, perhaps. And then the x squared goes inside. This would give us a square root of x cubed plus 3x squared dx, which is fine, but I don't really know what to do with that. So this, you could think this, but I think it's kind of a dead end, or maybe some kind of trickier substitution than we're going to do. So sometimes you try substitute, or you try sort of manipulating integrals in certain ways, and they just don't work out here. If you let u be the thing underneath the square root, so let's try that. U equals x cubed plus 3x squared. You get a square root of u, which you could integrate, but the problem is du is now 3x squared plus 6x dx. And you don't have this sort of factor with the x's there. So I'm not sure where to go. So this whole thing kind of doesn't work. So instead, what I'm going to do is kind of do a trick, which I kind of sort of referenced over here. And that's when I have a square root and you're not sure what else to do, sometimes letting u equal the thing under the square root tends to be useful. So I'm just going to try that. This looks almost too simple here. So I'll do u equals x plus 3. Well, then du is, well, 1 times dx, which is just dx here. So du is dx. Hardly looks like we're doing anything at all, but let's see what happens here. Now we got that x. Let's worry about that in a bit. Square root of x plus 3 is square root u. Dx is du. But then we have this x here. So what's x in terms of u? Well, what we can do is we can take our u equals x plus 3 and solve for x. So you would subtract 3 from both sides, and you get an x is u minus 3. And so in place of this x, I can get a u minus 3 there. So this will work out sort of just fine. Now to integrate this, well, I can't really do that directly, but I can now distribute this square root of u here. Now I could have tried that up here, but I have sort of 2 terms under the square root, and it kind of messes up this distribution step here. So what I'm going to get is u times square root of u. That's u to the 1 times u to the 1/2. That'll give me u to the 3/2. And then minus 3 u to the 1/2, or 3 square root of u. So I end up with that inside of my integral du. And now this is essentially, I can just use a power rule to integrate this. So u to the 3/2 integrates to u to the 5/2 divided by 5/2 minus 3 times u to the 1/2 integrates to u to the 3/2 over 3/2. And I should get my plus c. Now, we should do a few things here. One is simplify these fractions a bit. Dividing by 5/2 is multiplying by 2/5. So I'll get a 2 u to the 5/2 over 5. Here the 3 and the 3 actually cancel, and the 2 will end up on top. So I get a minus 2 u to the 3/2 plus c. And you might think, okay, now I'm done, but the answer here is in terms of u, whereas the original integral is in terms of x. So we need to plug x's back in. And so what we'll get is 2, see, u was x plus 3 to the 5/2 over 5 minus 2 x plus 3 to the 5/2 plus c. And this expression, I mean, you can make arguments for trying to simplify this in certain ways here. Like, for instance, I mean, I think I'm fine with this as an answer, but let's just look at what you could do. I made a mistake here. Not to the 5/2, to the 3/2. I just copied that over wrong. And so if we're going to simplify this, things you could do. Let's say I could factor out, let's maybe do this in some kind of blue here. So I'll say factor out a 2 here. I could do that. So I have the 2's here. I can also factor out an x plus 3 to the 3/2. And when you do that, what I'm going to be left with is an x plus 3 over 5. And then this is going to be 2x plus 3 to the 5/2, just minus 1. Here. So you could do something like that. I could kind of factor out the 1/5. Not entirely sure how well this is going to work out. Here over 5. And I'm left with, let's see, x plus 3 minus 5. So you could write, and I'm losing my plus c's as I go along. And so I could end up with 2 times x plus 3 to the 3/2 over 5 multiplied by, I guess that'd be x minus 2 plus c. So you get something like that. It's not at all necessary to move beyond this sort of first black square here in sort of my opinion, but it's nice to be able to do these sort of simplifications or transformations here, because you may be looking at an answer where you get this kind of an answer and you're trying to figure out, is that the same thing as what I have here? One more. So this one, I'm going to look at another square root situation. So square root of x plus 1 divided by x to the 5th dx. Now, this one, I think I'm just going to show the trick here, because you might try and let u be x plus 1, u be x to the 5th. These things tend not to work out that well in that scenario. So what I'm going to do, first of all, is I'm going to split my x to the 5th here, sort of fit a pattern that sort of I've seen before. I'm going to split my x to the 5th into x, about x to the 4th times x. So I split the x to the 5th into an x to the 4th and an x. Now what I'm trying to do is I'm picking the x here to match the x on top here. That's really what I'm looking at. And then what I'm going to do, I can pull out the 1 over, well, square root of 1 over x to the 4th here. And then I'm left with square root of x plus 1 over x. So I'm just doing some algebra here. Now 1 over x to the 4th, the square root of that's going to be 1 over x squared. Everything's positive, so I don't even have to worry about sort of domain issues. I guess I can't have x equal to 0. So I'm going to get 1 over x squared. And then I have a square root here. Now x plus 1 over x, what I'm going to do is take this and write it as x over x plus 1 over x. So sort of split that numerator up, or split the fraction up into two separate fractions. I need my dx. So I get an integral of 1 over x squared, and then I have a square root of 1 plus 1 over x dx. So right now it may not look like this is really accomplished much or is helping, but we can apply a trick that we did before and things are going to work out just fine. So one thing I'll do, particularly with big expressions here, is let u be the thing under the square root. So I'm going to let u be 1 over 1 plus x. I'm just hoping this works out. Du, 1 doesn't have a derivative, 1 over x, so that's, let's just rewrite this as 1 plus x to the negative 1. So I get a negative x to the negative 2 dx. But x to the negative 2 is just 1 over x squared. So I get a negative 1 over x squared dx as du. Well, that's pretty convenient because we already have the 1 over x squared here. We don't have the negative, but we can multiply the inside and outside by a negative to create that. So let's do that. So I get a negative. I'm going to write the square root first so I can put all of my du together. And then this will just be multiplied by negative 1 over x squared dx. So I'm pulling the 1 over x squared out in front, and then this negative and that negative would cancel out. And I sort of introduce those to get the negative to match my du. So we did some manipulation with our original integral. We got down to here, and sort of I knew to do that because I've seen this kind of problem enough times before. It's probably a tricky thing to come up with on your own the first time. And then what we did is we sort of did a certain u substitution, and we've got here. And now what I'm going to get is negative integral, square root of 1 plus 1 over x. Well, that's square root of u. And the second bit here, that's really just our du. And so square root of u is u to the 1/2. So when I integrate this, I get a negative u to the 3/2 divided by 3/2 plus c. Dividing by 3/2 is like multiplying by 2/3. So I get a negative 2 u to the 3/2 over 3 plus c. And our answer cannot be in terms of u because it's sort of a variable we introduced. We want to change that back to x for an indefinite integral. And so we're going to plug in this u as 1 plus 1 over x. So we're going to get negative 2/3, 1 plus 1 over x to the 3/2 plus c. And that is our answer to our integral here. So just some more examples with this substitution. Again, I mean, the sort of straightforward questions, and then there's sort of trickier ones. A lot of times you have to sort of see the trick. I think there's some value to both being able to find those, but if even not being able to find them, there's some value to be able to follow along and understand what's going on. So if you're reading some physics book later on or something, you can see, oh, we did this substitution. You can kind of say, okay, that's right, or maybe it's not right.